This video is the second video for optimization. So now we're going to increase the level of difficulty of these optimization questions a little bit. And how we do that, we are not given the function that we want to optimize initially. So a lot of the IB questions that are given to us, they ask us to first find the equation that we want to optimize. So depending on what is given to us, we first need to identify some variables. And then we need to create this function. Now, this is super important. The function that we create is what we want to optimize. So in the question, they'll say, we're trying to optimize the area, or we're trying to optimize the volume, right? So this function that we create, it must contain only one variable. You'll see in some examples that we do today, it is possible that there are two variables that exist in the question, and therefore we have to create two equations. But in order to use the following steps, which is the steps you saw in the previous video, we need a singular function that has only one variable. So the step of substitution from having two equations to substitute the variable of one into the other often needs to be used with these types of questions. And hopefully this makes sense in the questions that you're going to do in this video.
First example, a square sheet of card with 12 centimeter sides has 4 squares of side x centimeters cut from the corners. The sides are folded to make an open box. Find an expression for the volume of the box in terms of x, and then B, find the value for x for which the volume is maximized, and prove that it is a maximum. Okay, so for this example, the first thing we need to define is x, which is actually already defined for us. In the picture, you see the side x are these sides right here. So that's done. Part 2, we're going to create a function. Now our objective is to maximize the volume, so I need to create an equation for volume itself. Now the volume is going to be the length times the width times the height of our box. So we're going to use the x in order to find out what that is. Let me zoom in here. So we have the height of our box is the value for x. So the height of our box is going to be the value of x. Next, if we talk about this side of our box, well, this side of our box is going to be 12 minus x minus x. So we're going to have 12 minus 2x, which is actually the same as the other side, 12 minus 2x. Okay, so we have our height and we have our width of our box. So the volume is going to be x times 12 minus 2x times 12 minus 2x. Awesome. Now that we have a function, we now need to do step 3, which is to differentiate our function. Well, differentiating our function, we're going to need to first rewrite this expression so that it's in a form that we can actually differentiate, meaning we need to have x to the power of something for all of our terms. So if I distribute the x, I'm going to have x, and then I can use FOIL to expand this. So when I use FOIL to expand this, we're going to get 144 is 12 times 12 minus 24x minus 24x plus 4x squared. And then we can simplify even further. And now I can do the last step, which is to distribute the x. So I have 144x minus 48x plus 4x cubed. Now this is all the volume function, and now I'm going to be ready to differentiate the volume. So the derivative will be 144 minus 48, this was an x squared, apologies, so times 2x, and plus 12x squared. Now the objective is to find the maximum volume. So in order to find the maximum volume, I need to find when is my derivative equal to 0. So I'm going to ask myself, when is 144 minus 96x plus 12x squared equal to 0. And I'm going to use my calculator for this. Now there's a few ways that we could find it using the calculator. You could put all of this into the apps simultaneous equation, polynomial root finder, or what you could do is you can graph the function and you can find the zeros, and that's what I'm going to do, but feel free to use your app's polynomial root finder. If I go on my graph, I now see the two values, which will be my zeros. So I can go second function trace, zeros, and I'm going to repeat the same thing for both of the zeros. So to the left and to the right of it. And I'm going to get that one of the 0 happens when x is equal to 2. And the other one is going to happen at the other point when x is equal to 6. Now one of these will be a maximum and the other one will be a minimum. You can use your understanding of functions that we did last class, and we can know that since we have graphed the derivative function, then since the derivative goes from positive to negative when x is equal to 2, so it goes from being positive to being negative. Let me write that down here. And then for x is equal to 6, the derivative goes from negative to positive. So if we think what that means for a function, if our function had a positive slope, that means it was increasing, and then it went decreasing. So at x is equal to 2, we're going to have a maximum. And for x is equal to 6, we had our function was decreasing and then increasing again. So this would be a minimum point. So when we're looking for what is the volume for the maximum, well, we're going to be using x is equal to 2. So since our x is equal to 2 is our maximum, then we can find out what the actual volume is. So our volume is going to be 2 times 12 minus 2 times 2 times the same thing. So when you put this into your calculator, you're going to get that the maximum volume is 128 centimeters cubed. Example 2. A farmer has 400 meters of fencing. The field comprises 2 small pieces, 1 rectangle and 1 right triangle, which are attached as shown in the figure. The fence will be placed along the solid blue perimeter of the field. Find the length of x that gives the largest area of the field. Okay, so we have our x, which is defined here as the length which is here, which is also the same as this one here. And we also have y's that are defined. Now, our first objective is going to be to create a function for what we're trying to optimize. So our function always needs to be about what we're optimizing. So the area is what I'm optimizing. So I need to create an equation for the area. Now the area comprises of a rectangle, which the area would be x times y, plus a right triangle, which has sides x by x. So we're going to have x times x divided by 2. So the equation for area of a triangle, 1/2 base times height. So this is the equation we have for area. Now, our step 2 would be to find the derivative of this. However, we're kind of stuck because we have 2 variables in here. We not only have x's. So what we need to do instead is we need to find a way to express y in terms of x, and then I'll be able to do the derivative. So super important here, since we have y, we need to find an expression for y in terms of x. And this is where the 400 meters of fencing is going to come in. So the fencing is all my perimeter, and my perimeter is going to be x plus y plus x. So what I've done so far, I'll put it in red, is this added together. And we still need to find this side here. Now this side, I can use the Pythagoras theorem, and I'll find that this is going to be the square root of x squared plus x squared. So it's going to be the perimeter equation. And all of this perimeter should be equal to 400. So we're going to have 2x plus 2y is going to be equal to the square root of 2x squared. Plus 2y plus the square root of 2x squared. What I'm going to do with this, I'm going to rearrange it so that I can have y all alone on one side. And I get 400 minus 2x minus the square root of 2x squared is going to be equal to y, 2y. And next step is to divide everything by 2. So I'm going to have 200 minus x minus the square root of 2x squared, all this squared, is going to be equal to y. So now this whole thing can replace y in my original function. So all of this is going to be placed as y in this equation. So I'm going to have that the area is going to be equal to x times 200 minus x minus the square root of 2x squared divided by 2 plus x squared divided by 2. Okay, so this is going to be the equation for my area, and now I can use this because my objective is to optimize the area. So since I want to optimize the area, I need to find the derivative of the area. So before I can find the derivative of the area, then I can write everything in terms of x to the power of something. So I have that the area, I can distribute the x in front of the brackets, and I'm going to get minus x square root of 2x squared divided by 2 plus x squared divided by 2. What you can do is you can find the derivative of each of these terms first, or you can simplify by combining like terms together, as you wish. I'm going to combine my like terms together to start. So no differentiation yet for me. I'm going to simplify this equation. So I have, let me change colors, the square root of 2 times x squared. So the square root of 2 times x squared, that's the same thing as saying square root of 2 times square root of x squared. So that means that these will cancel out. And I'm going to be left with x times the square root of 2 times x divided by 2. And then I can add negative x squared plus a half x squared, and that's going to be negative x squared divided by 2. And now I'm ready to differentiate. So the derivative of this whole thing is going to be 200 minus 2x divided by 2 minus the square root of 2 times 2x divided by 2. So a few things can cancel out. These 2's will cancel out. And I'm going to be left with the derivative is equal to 200 minus x minus the square root of 2 times x. And now I can find when is this going to be equal to 0 using my calculator. So in my calculator, I can put this either in numeric solve, or I can put it as a function. So let me put it as a function. I'm just going to remove the one that we did previously. 200 minus x minus the square root of 2 times x. And I can graph this. If I don't see it, then I can zoom out. 3. There we go. And now we see our function. Our objective is to find when is this equal to 0. So we're going to find the zeros of our function. So there's only one 0 here. So I'm going to go to the left of it and to the right of it. And then we're going to guess. And we get that our derivative is equal to 0 when x is equal to 82.8. So they're asking us find the length of x that gives the largest area. Well, there's only one place where we have our derivative equal to 0, and that is when x is equal to 82.8.